So let's talk solute-solvent interactions. And again, when we're talking about solvents here, we are talking about aqueous solutions, right? So this is a conversation that can now be framed as presuming when we're looking at a polar solvent, we are looking at water. So what is going on between one type of solute, here the ionic solute, that the polar solvent water can dissolve? Like what's happening in terms of the interactions between those solute and solvent particles that allow for these things to create a solution? So let's remind ourselves about the 3D geometry of water and why that means it's polar. And something that's also kind of special about water, like it's not just polar, it's also kind of like crazy polar. So we'll talk about why. So water, H2O, has a geometry that is bent. So using our perspective sketch, wedge dash notation, the wedge indicates a hydrogen that is sticking out of the screen toward you. And the dash indicates a hydrogen bond that is sticking back behind you. With these two lone pairs on oxygen, this is a bent molecular geometry. And if we were to identify each of these bonds that exist between hydrogen and oxygen, both of these would certainly be polar covalent bonds. So polar covalent bonds. And if I wanted to represent those dipole moments, they would be angled at around 109 degrees up toward the oxygen, with regions of partial negative charge near that oxygen, leaving regions of partial charge down toward each of the hydrogen atoms. So what does that mean about the overall polarity of the water molecule? So just redrawing this structure. Notice both of these dipole moments are pointing up. Like if I were to break these vector up into their components, I would have some kind of upness for both of them. And the one on the left is pointing to the right, and the one on the right is pointing to the left. So these moments or aspects of that vector would cancel one another out. However, the upness quality of these vectors would not cancel one another out. So overall, we have a net molecular dipole that points straight up through the water molecule toward the oxygen. Now, remember, hydrogen is very poorly electronegative. It's very weakly electronegative. And the reason for that is because a hydrogen atom is simply a proton and an electron. So if electronegativity is related to how strong of a pull the positive nucleus of an element has on the electrons it's sharing with something else in a bond, then hydrogen's pull strength is going to be really weak, right? It's just one singular proton compared to something like oxygen, which has multiple protons and it's all pulling on electrons that are around its own self in that second energy level, n equals 2. And then also those electrons it's sharing in the molecular orbital in the bonds it's forming with hydrogen. So what on earth did I just say? What I just said is that the difference in the electronegativity of oxygen and hydrogen is large. So water has a very strong molecular or net dipole. This is why you might have heard water be referred to as the universal solvent, because water isn't necessarily limited to the phrase we discussed earlier here when talking about solubility, which was like dissolves like. Because if we were to just follow that rule on its own, what that would mean is that water, since it's polar, can only dissolve polar substances. And we know from our own lived experience that that's just not true, right? So let's look at this example here of the process of sodium chloride solid being dissolved. Probably move that, it's a little squished. So sodium chloride solid in the presence of water being dissolved. So how is it that a polar substance, especially water, this incredibly polar substance, can dissolve something like a solid ionic substance, which are typically very stable, right? Think about ionic compounds in general. Those are crystals, right? We've got this super dense packing that forms what we call like this overall crystal lattice structure due to the ionic bonding that's happening between the metal cation and non-metal anion here. So what's going on in terms of the interaction between water and these ions in the crystal of sodium chloride that allows sodium chloride to be dissolved? So let's write out what's happening. So as shown in the diagram, we see, and we know from experience, that if you were to take a crystal of sodium chloride and add it to water, you would in fact generate ions of sodium and chloride, which are now separated, meaning their ionic bonds have been broken. Why have those ionic bonds been broken? Like, what is it about water that allows it to do this? Like, why can't it disrupt the ionic bonding, which is pretty strong bonding between these two substances? Because water is such a strongly polar molecule. What we find is that the lattice energy of the sodium chloride crystal, which is the energy that is holding our ions together in what we call the bulk solid, or the big crystal of this solid, has to be a less stable form than what is labeled here as the hydrated version of these ions, meaning the energy that keeps these ions packed together in a crystal is really not as stabilizing an energy than the energy of what we call hydration. Where hydration refers to the process of these water molecules connecting to create what we call like a sphere of hydration. Where all of the dipoles, so here we've got like a little partial positive dipole on water, are going to align themselves to attract to the ion that has an opposite charge. So if we're looking at this little partial positive down here, that is going to be attracted to the negative charge of the chloride anion. So when these water molecules surround your ion, that's called a sphere of hydration. And in the case of sodium chloride at room temperature, this must be true, right? We observe that sodium chloride is very easily dissolved in water. So this means that the energy of hydration, or the state of our ions being hydrated or solvated, is more stable than the lattice energy. And as a result, our ionic bonds are disrupted. And now we have ions in solution. Now let's look at the title of this slide. Solute-solvent interactions. So what is happening here with respect to thinking about like how these particles are interacting? Now, in a nutshell, any kind of interaction that we're going to talk about between particles in a chemistry course is always going to be related to charge. Always. We're asking ourselves, like, what kind of charge stickiness do these substances interact with or exert on one another? So looking at this example of our hydrated sodium and chloride ion, we see that we've got the dipoles of the water compound that are aligning with the ionic charge of the ions. So very creatively, we call these ion dipole interactions. And we do have a name for interactions that's a little bit more specific. We call these intermolecular forces, or IMFs. So when talking about what's going on that allows a polar solute to dissolve an ionic compound, it's got to be ion dipole intermolecular forces that allow for this to be true. If those ion dipole intermolecular forces are ones that do not create a more stable system for our ion, when our ions are hydrated compared to when they are bonded in a lattice, then we are insoluble. And we've seen some examples of insoluble things based on our solubility rules in Gen Chem 1. Now, solubility in general, specifically like ionic solute solubility, is something that we're going to have a more intense conversation about when we start talking about phase equilibrium and saturation and a bunch of things that you probably don't know about yet. But for now, this is kind of just like a good recap of thinking about intermolecular forces, the role that they play in the process of dissolution, and also understanding why it is that water in particular, a very strongly polar substance, can dissolve not just other polar substances, but also ionic substances, ionic solutes, for example, like sodium chloride. So in our next conversation, we're going to talk about something that's a little bit less complex than this, right? Like we're talking here about, the special case of water being really polar and how it can dissolve ionic solutes. In the next slides that we'll write out, we're going to be going back to like the basics of like dissolves like, where we're going to be thinking about the interactions between polar solutes and polar solvents, and then also contrastingly, nonpolar solutes and nonpolar solvents. So asking yourselves, what are the intermolecular forces that are allowing for a polar substance to dissolve another or a nonpolar substance to dissolve one another? Now let's think to ourselves about what kinds of substances water can dissolve, right? So are we limited to just dissolving ionic compounds in water? So when I think about this, I think, yeah, okay, yeah, I dissolve table salt in water. I've dissolved Epsom salts in my bath, right? But I've also dissolved other things like sucrose, right? And sucrose is not an ionic compound. That's made of carbon, hydrogen, and oxygen, all nonmetals. So what's going on when we have solutions that involve not ionic solutes, but polar solutes in polar solvents? So I've got an example here of a solution where we have ethanol. I'm going to abbreviate ETOH in water. And this is what you would find if you were to look at a bottle of Grey Goose, right? Or a bottle of vodka, right? Drinking ethanol. Or if you're a biologist, maybe work in a microbiome lab, you've probably used ethanol to clean your benches before. So ethanol here is our solute, and it has the following structures. So it is shown, let me kind of highlight it. Let's do pink. Here's 1 unit of ethanol. So ethanol is our solute. It has the following structure. So we've got a carbon bound to a carbon, bound to an oxygen, bound to a hydrogen. And we've got a local tetrahedral geometry around the carbon that I've kind of now shown here on the left. So I've got to draw in my hydrogens using my wedge dash notation. I've also now need to show the local geometry around this central carbon. So that's 1, 2, 3. And then somewhere in the back, there's got to be a fourth one for, you can see over here, right? 1, 2, 3, 4. Just following octet. And then our oxygen is going to look very similar to how it does in water. It's going to have 2 lone pairs causing an overall bent geometry. Now, if you're asking yourself, like, where did my 3-dimensionality go? When you draw your structure this way, you're implying that your electrons are sticking out of the page and also receding backwards. So they would be like this right now, looking at us. And let's just kind of confirm with ourselves that we agree that this is an overall polar compound. So I notice here that oxygen is very electronegative. It is up in that upper right-hand corner in row 2, up near fluorine, right? So this has a very strong effective nuclear charge that's going to draw electrons that it's even supposedly sharing with another substance closer toward itself. So the electron cloud is a lot more dense around that oxygen due to its electronegativity. And then over here on this other side of the molecule, we've got a bunch of carbons and hydrogens, which, yeah, I mean, carbon does have some electronegativity, but compared to oxygen, it's very weakly electronegative. So this is very non or weak electronegativity. So what does that mean for us in terms of if our solute is polar? So because we have this disparity of charge, meaning we've got a region where electrons are being drawn toward, and electrons are negative, and a region where electrons are being drawn away from, then because we have those negative particles being drawn toward this end of the molecule, we're going to have kind of like a lopsidedness in how those electrons are distributed across the molecular orbital. So we would say that we've got a net dipole across this molecule pointing toward the oxygen. So this is, in fact, a polar solute. Water in this solution is our solvent. Again, we're kind of going to be focusing on aqueous solutions. And as we saw from before, water has a very strong dipole due to the fact that it has set up a bond between hydrogen and oxygen. So here's our water there. And if we're thinking about this in a general sense, Because we know this substance is going to be polar, so our solvent, is also polar. We know that we're going to be looking at overall dipole interactions. So these are called van der Waals forces. It's another way you may have heard of these. And you'll notice that on this board, there's something written that we have not really talked about yet, which is this idea of a hydrogen bond. So a hydrogen bond is not a bond in the sense that electrons are not being shared between two atoms, so there's no covalency, nor are electrons being donated or accepted, so there's no ionic bond that's happening. However, hydrogen bonds are referred to as hydrogen bonds because they are a type of dipole-dipole interaction that is incredibly strong. So hydrogen bonding. Hydrogen bonding is the super strong or strongest dipole-dipole interaction. And this is just due to the strength of the overall molecular dipole, because we are looking at dipoles that are established or brought into existence by hydrogen, which again is like incredibly weakly electronegative, and are very electronegative substances like oxygen, nitrogen, and fluorine. So anytime you have a compound that lacks a three-dimensional symmetry and also contains bonds between hydrogen and these three very electronegative elements, then we're going to set up really, really strong dipoles near those polar bonds across the molecule. And we're going to see the phenomenon of hydrogen bonding, which is what's highlighted here for you with these little green dashes. So what is it that is allowing the water to dissolve the ethanol? It's not that the ethanol is breaking up into pieces like we saw with our sodium chloride, but rather we've got enough charge stickiness due to these hydrogen bonds that are set up between our molecules, because they are both very polar and they both have bonds between hydrogen and something electronegative like oxygen, that allows for these two things to mix and create a solution. All right, so ionic substances, we've got a full splitting up of our ions. We're looking at an ionic charge attracted to a dipole. Rather, now when we're looking at solute-solvent interactions between polar solutes and polar solvents, we are looking at dipole-dipole interactions or van der Waals interactions, with a special note to keep your eye out for hydrogen bonding, especially since we're talking about aqueous solutions. All right. We have now covered what kind of solute-solvent particle interactions exist when we're looking at a solution that's composed of an ionic compound and a polar substance that's a solvent, excuse me. And now we're looking at polar solutes and polar solvents. Those are not the only kinds of solutions that we can make. It is possible to make a solution of nonpolar solutes and nonpolar solvents by mixing something like a nonpolar liquid into another nonpolar liquid, which is going to be your entire life in organic chemistry. So the question kind of comes to us of like, how is it possible? So how can a nonpolar liquid, quote unquote, dissolve another nonpolar liquid? Because it was pretty evident when looking at things like polar solutes and polar solvents and ionic solutes in polar solvents that we were looking at some really strong charge interactions, either between an ion and a dipole or between two dipoles themselves. So it was innately a charge interaction. Now, when you hear nonpolar, you're probably thinking no charge. And you're right, right? Nonpolar substances have no net dipole across the molecule. So again, then how is it that we can maybe get some kind of charge interaction like we did in our other types of solutions for things that inherently have no charge? So this is where what we call dispersion forces come into play. So what is a London force, a dispersion force? It is a type of dipole-dipole interaction. However, it's a very, very weak one, and it's one that is found in like everything. So let's talk about it. Dispersion forces. These are intermolecular forces that are resulting from an induced dipole, meaning like a dipole that was created as a result of some precipitating event. So, what is that precipitating event? Like, what would cause the electron cloud or the molecular orbitals around one molecule to now kind of slightly get skewed so that there's now a little bit more electrons on one end compared to another? And the answer is randomness, chaos. Nature is full of randomness and chaos. So we have to remember, like, what is an electron cloud? What is an orbital? An electron cloud or an orbital is basically just like a region in space where we're pretty sure, according to quantum mechanics, we're gonna find an electron. So sometimes, just due to natural fluctuations in the nature of like that electron existing in that probability cloud, sometimes we have these small natural fluctuations in our electron cloud density, because again, our orbitals are inherently like a probabilistic concept and construct. And if we look at this image here, what you're seeing is this idea of something having been induced or one fluctuation causing another. So let's kind of look at these dipoles that they've drawn here. So normally these substances would have an electron distribution perfectly even across the molecule. Like if this is a non-polar substance, then on average, there's going to be like no difference or no discrepancy in the electron cloud density. However, let's say that just due to random circumstance, this particular molecule, let's call it molecule A, decides, you know what, I'm going to be a little wonk. I'm going to be lopsided. I'm going to have now a partial negative because I've got my electrons kind of thrown over toward one side of my molecule, and a baby partial positive because my electrons have left their original position. And now I have what's called a like random dipole that's been set up. Because molecule A underwent this, statistical natural change in its electron cloud density, which happens for just a moment, its neighbor, because remember, molecules are pretty close to one another, is going to then respond to that charge in kind. Because you can imagine if I've got molecule B right next door to molecule A, and molecule A decides that it wants to have, for just a hot second, this disparity in charge, creating a momentary dipole, then the electron cloud around B is going to respond to that momentary charge because, again, the electron cloud in B is just where we find our electrons, which themselves are charged. So if I've got now like a partial negative on one end of a molecule nearby another molecule, these electrons are going to, in turn, create their own dipole in an effort to try to repel from one another and put positive charges next to negative. So these are both innately, originally nonpolar substances. However, due to like random fluctuations in one, a dipole can be created in a molecule and then induced in its neighboring molecule. And this is a constant process that happens like over and over and over again. So it's a constant, short-lived process. And as you could imagine, these intermolecular forces, meaning these dispersion forces, these induced dipole moments, are more pronounced, meaning like they're more statistically likely to happen as the size and overall surface area of the molecule increases. So in our example here, looking at molecule A and B, we're looking at probably something that's just, a little homonuclear diatomic, like maybe, I don't know, N2 gas. But if we're looking at some big, disgusting organic molecule, sorry, Dr. Puenzo, then you can see, like, if I've got carbon here, carbon here, carbon here, carbon here, carbon here, 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 and then a bunch of hydrogens to fill in my octets, this is a decently large electron cloud, which means that I can have micro fluctuations in that electron cloud density happening at a bunch of regions in this molecule at once, meaning I'm going to have a lot more little micro stickiness that's going to allow a substance like this to have some kind of charge interaction or charge attraction to another nonpolar substance that also has these little micro stickiness moments happening. So when talking about solute-solvent interactions between nonpolar substances, this is all purely due to our London dispersion forces, or the idea of like these short-lived induced dipole interactions. All right. This is an extra slide. So what we're going to do is we are going to look at a solution at a molecular level. And this is a solution that is aqueous. So let's kind of identify what we're looking at here. So here, this guy here in yellow, this is H2O. And I know it's a little hard to tell, probably because we're not super familiar with our organic structures. But this guy is ethanol. So this is the substance that we looked at earlier on when talking about polar solvents and polar solutes. So in this practice question, we're asked to describe this solution. So it's a solution, an aqueous solution. that is composed of water and ethanol. And the first question is, what is the solute? So how do we answer this? What we're really asking here is what's present in the larger amount, or what's doing or causing the dissolving. So if we look at our little zoomed in version of what's going on in this beaker, if we were to just count our waters, right? So let's go ahead and do that. 1, 2, 3, 4, 5. That's a water. 6, 7, 8, 9, 10, 11, 12 waters. And then compare that to our ethanol. 1, 2, 3, 4, 5. We see that the amount of water is more in solution than the amount of ethanol. So number of H2O molecules is greater than the number of ethanol molecules. So this allows us to answer what is present in the larger amount. This has to be our H2O. Oh, I have this backwards. Solute. So solute, this will be what is present in the smaller amount and what is dissolving. Sometimes I can read. So smaller amount and what's dissolving. Solute. So in this case, then our answer would change to ethanol. Ethanol is the solute. It is present in the lesser amounts. It is what is being dissolved by the solvent, which means that whatever is present in the larger amount this is our solvent, which is our water. All right, question 3. Is the solute ionic, polar, or nonpolar? So I'm going to re-sketch out what ethanol looks like. So ethanol again was CCOH. Like so. Notice this composition is carbon, hydrogen, and oxygen, and these are all nonmetals. So we know that we cannot be ionic because we are composed of only nonmetals. And now the question is our solute polar or nonpolar? So you can think about this in a couple of ways. 1, was it dissolved by a polar solvent? Yeah, we know that water is polar. So therefore, if we're following the like dissolves like rule, then our solute must itself be polar as well. However, let's prove that to ourselves by looking at the structure of the molecule. So just like we did earlier, we looked at the electron cloud distribution in this molecule. We recognize that we've got this very, very polar hydrogen-oxygen bond that is going to cause our electron cloud to be kind of bulging around that oxygen due to its very strong electronegativity. This is going to establish an overall net molecular dipole with the partial negative charge pointing toward the oxygen. And that dipole that is set up is so strong that in fact it's going to create these charge interactions between the solvent particles, water, that are not just dipole-dipole interactions, but are hydrogen bonds. So if we're going to answer this question, we know that this solute has to be polar. Okay. So that's the basics of how we think about solutions in terms of what they're made of and how those components of solution interact with one another. So in our next video, we're going to talk about how we as chemists quantify inherent properties of solutions. And these should be concepts that you've heard of before, namely the idea of solution concentration with the unit that we've been using, molarity, and also the idea of solution density. So that's what you can expect in our next lecture video.